Hi, this is Mark. Welcome again to another short video tutorial, and this time we're going to talk about Boolean algebra. Boolean algebra is a form of mathematics, a form of algebra that's applied in the digital world. From the term alone, Boolean, that means you only have two values. In the discussion of Boolean algebra, this will just be short. We'll be covering basic Boolean equations, multiple level logic representations, basic identities, algebraic manipulation, and complements and duals. So the founder of Boolean algebra is no other than the person himself, Mr. Boole, by the name of George Boole. He's a professor at Queen's College, Cork, Ireland. In the spring of 1847, he put his ideas into the pamphlet called Mathematical Analysis of Logic. Under basic Boolean functions, we have here examples of gates or functions, which we have discussed on the previous tutorial. First one is AND. We have the OR and the NOT. These are basic gates. If it's AND, this is just a sort of review. So Z is equals to AB. X is equals to CDE. Okay, so there are three. That means there are three inputs. You have two inputs. For this, you have four inputs. F, G, H, K. And your output is Y. Now, for an example for OR is this one. A or B. Okay, you have a plus sign in between which will denote OR. For the for the end, if you don't see any symbol in the middle, that is assumed to be AND. Okay? So or is you have a plus sign. So you have how many inputs do you have here for Z equals to A or B? You have two inputs. For Y, you have how many inputs? Of course, you have F, G, H, K. You have that's four inputs because one, two, and three, and four. Okay? And finally, now for not, Z is equals to not A. So if the value of A here is 0, so not A is equals to 1. But if the value here of A is 1, so the value of Z here is, of course, the other. If it's 1, so it's going to be 0. Okay? So for this one also, the end result for F and G and H and K, whatever it is going to you're going to get the opposite of that. If the end value for F, G, H, K is 1, so the value of Y is 0. But if the value of the final value for A, F, G, H, K is 0, so your value for Y is 1. Consider the following logic equation. Z ABCD is equals to AB plus CD, or AB or D. I'm sorry. AB or CD. Okay. The Z ABCD means that the output is a function of four variables within the within the parentheses. So the ABCD are the four variables involved. Then the AB and CD, this one, are the terms of the expression. Okay? So this form of representing the function is an algebraic expression. So it's now a Boolean algebraic expression. For this function to be true, either both A and B are true, or both C and D are true. Okay? So we will understand all the more with the next slides. So this is what the truth table would look like, or the logic gate for this one, for the Z A B C D is equals to AB or CD. Okay, this is AB or CD. That's why AB or CD, and which is A B A and D Okay? And then C and D, they will be ORed, A, B, or D, and you have the Z. Okay? So you can we can verify this with the truth table, okay, here. So you will only have the Z to be 1, okay, during this parts here that you have 1. So this is the CD are ones here, the ABCD are 1, CD are 1, okay? So in other words, you will have the Z as the output as 1 if and only if you must have at least 1 in the AB or the CD or a combination, so that you'll have a 1 for Z. Okay? So that is the interpretation based on the logic gates to a truth table. That is why it is very important that you express your Boolean algebraic expression to a logic gate and then express it also to a truth table, so that you'd be able to see the outputs based on the combination. Okay? So if A, B are a 0, 0, and then C, D are 0, 0, also you have 0. Okay? So if you have A, B 0, and C is 1 here, C is 1, and then D is 0, you will have 0. Why? Because your C, 1, 1 and 0 is always 0. For as long as you have a 0 in the AND operation, remember, the output will be 0. Okay? So I hope you understood this. Let's proceed. Some examples of function or f is equals to ab plus cd plus d prime, or not d. Okay? Remember, the prime here, you can also express that into a bar. You have a bar here on top or a prime, that's the same. Okay, so y is equal to cd plus a prime b prime. So sum is equals to, these are examples of Boolean expressions. Okay, these are examples of Boolean expressions. And equations can be very complex, from simple to complex, and usually desire a minimal expression. Let's proceed now. So these are the basic identities. And you or any variable to 0 will always be itself. Okay? So same is true with for and you end any variable with 1 will always be itself also. Okay? Okay. So for the basic identities of Boolean algebra, we have here the first one, which is x or 0 will always be x. That means any variable that you have and you OR it with 0 will always have the same identity. Okay, so if your a here is 0 and then you OR it with 0, will always be itself. Okay, so 0, 0, 1, 1, because you use the OR. And for the end, you end any variable with a 1 will always be itself also, if it's and 1. So if it's you or a 0 with if you end a 0 with a 1, will always be 0. If you end a 1 with a 1, will also be 1. Okay, it's like um any number multiplied by 1 is itself. Okay? So for this one also is any number you plus with 0 will always be itself, because it's just 0. Okay, something like that. So the next one is x or 1 is equals to 1, because any number you any variable, whether this is 0 or 1, the value will always be, the end value will always be 1. Okay? If this is 1, 1 or 1, that's 1. 0 or 1, that's still 1. Same is true with the other, on the end side is, if you end any variable with a 0, will always be 0. It's like you multiply anything with 0, it's always going to be 0. Okay, for the end. For if you, or a variable with itself will always be itself also. Okay? So whether it's 0 or 0, 0 or 0 will always be 0. 1 or 1 is also 1. So for the end part, also end, the end one, so x and x will always be x. So whether this is 0 or 1, so 0 and 0 is 0. 1 and 1 is 0. Okay? So that is for the first 6 identities. We're going to move now to the next identity. So the any complement or the opposite of a variable. So if this is 1, since you have the apostrophe here, it's the complement of 1. That means it's 0. So it's like 1 plus 0, or 1 or 1 will always be 1, because you always will have a 1 if you talk about or for variable and its complement. Okay, so if the, see here, if the x is 0, the complement of x is 1. If the x is 1, the complement of x is 0. So if you OR that, it always has a 1. So that's why your result will be 1. So on the other side, on the other end, which is the end, if you end any variable with its complement, that means if this is 1, so the complement of 1 is 0 because of the prime. So 1 times 0, it's like you multiply. 1 times 0 will always be 0. Or if it's the other way around, if this is 0, so if you have the prime or the opposite, 0 times 1 is 0. Okay? So um, you may always think also that if you use the and, you're using the multiplication. You may think it that way so that you won't forget. On the other side, if you have a complement already and then you complement it, that what happens is you negate it, or you cancel the complement. So if this is 0, the complement of 0 is 1, and then another complement of 1 is 0, so it goes back to its original number or original variable value. So if this is 0, so complement and then complement again, or you negate it twice, so it cancels the negation. So you have this value. Okay, the variable itself. Next is, now we're going to talk about the basic properties. Remember, there's 10, 11, 12, 13, 14, 15. These are because we can identify in your solution how to simplify by using these numbers, by pointing out these numbers later on. So commutative law, x x or y is equals to y plus y or x. For commutative, if it's x, commutative is applicable for the and, commutative is applicable for the or. X and y is still equals to y and x. So for the associative, this is like a distributive. It's like some kind of distributive, but actually the next one is distributive. So x, y, for as long as they have the same operations, that means they are all or or they are all and, you can switch the parentheses. So x or parenthesis y or z parenthesis is equals to this one. So you just switch the parentheses, but you will have the same answer. So for that is associative for the or associative for the end. This is just the same. Even if you switch the parentheses, it's still the same. It's this the same because you have the same operation. Now comes the distributive. The distributive is when you there's a combination already of and the or. Okay? So for example, for this x, y, or z, what you can do to how you can simplify this is you distribute it. So x, y, you have here, or x, z. That is distributive. Okay? So the and distributes over the or. Okay? If this is how it looks like, this is how you distribute it. On the other end, if this is how it was, this is how it was, if this is the equation, you can distribute this, okay, by instead of this way, the or now distributes over the end. So x or y, this one, and then you put a parenthesis, and then parenthesis x or z. Okay? So that's the distinction between the distributive of this form and then the distributive of this form. Next is the famous De Morgan's theorem. And this is very important in simplifying equations. If you find that this always comes when you have a a negation or complement or an apostrophe or a bar. Okay? So the equivalent of this small apostrophe is equals to, actually, if there's a bar here on top of the quantity x plus y, is the same as this, because this apostrophe is outside the parenthesis. So this is actually equivalent to, it's like you are distributing the parenthesis, the apostrophe, to the x and y, but now you're going to change this into the opposite operation, which is the end. So the result now is this one, you distribute it to the x, this is distribute to the y, and then you replace this with the opposite operation. Okay, so that's why you have the end operation. So same is true with the other one. If you have this negation also, quantity x and y, so you distribute and then you replace this to or. So distribute, that's why you have uh, the x prime plus, because it becomes the end, I'm sorry, or from the end, and then the y prime. Okay, so this is how it looks like in the truth table. So you have xy, so you have x plus y, x or y, and then xy, x, not x or not y, not x, and not y. Okay, so if you hear the term always not x, is the same as an x prime, okay, or bar x. This means the same thing. Okay, it's a negation. Okay, so these are the possible combinations if you have this zero. Always remember this, that if you create a truth table, you represent all the combinations. So this is zero. This is zero zero is zero. Zero one is one. One zero is two, and one one is three. Okay, so this represents all the possible combinations. Okay, so next. So how do we simplify? This is an example of simplification using the identities that we have just discussed. So this is what's given, the x, not x, y, z plus, not x, y, not z plus x, z, which is, as you can see, this is apostrophe, but now here in the solution, we can also represent it this way. Both will will mean the same. Okay. So this was identified with this kind of operation of equation. We can see that we can use the identity number 14. Let's check what it is. Where's number 14? And that is the distributive law. Okay, let's go back there. How it looks like. So this is the distributive law. So from the you have since this is common, the not xy is common to these two terms, you now apply the distributive law. Okay, so that is why we get the reverse of, we remove the xy and then open close parenthesis the z and the not z, then plus xz. So next step is we can find that this particular identity is actually equals to 1. Remember, that is identity number 7. Let's take a look at now identity number 7, and that is this one. Any variable you OR it with its complement will always be equals to 1. Let's go back there, and that is true. So the z and not z is actually equals to 1. That's why the xy or I'm sorry, xy and 1 plus xz. So this is very familiar. If you end anything with any variable with 1, will become itself, and that is identity number 2. Let's go back. First identity. This is identity number 2. Any variable you end it with 1 will be itself. Okay? Let's go back there. And that is true. That's why you have this simplified as not x, y plus xz. So this is the simplest form. Okay, so this is your final and simplest form of the expression. So f now is equals to this long equation is now shortened to this term only. Okay, so that is how you simplify using the identities. Okay, so effect of the implementation. Let me move the picture. Okay, so if it was not simplified, this is how your logic gates would look like. There will be more logic gates compared to a simplified one. So the simplified one, you have lesser logic gates, but you will have the same result as the one with plenty of logic gates. With this, your your expression and your logic gates actually is more efficient, okay, with this, because you used lesser resources and lesser amount of time to be able to come up with the same as answer as this one with the longer equation. Okay, so it is better to first reduce it into its simplest form before implementing it to a logic gate diagram. Okay? So other examples are this. You have here x plus xy, and then you use the identity number 2, which is um, x, identity number 2, which is x plus 1, x, x is equals to x and 1. So that we can factor out, use this identity, we can factor out this. So we use the distributive law in number 14. Okay, distributive law, x 1 plus y, which if you have this will always be equivalent to 1. Okay, 1 plus y is all I'm sorry, 1 and y, 1 or y will always be equals to 1. That's why you now have the x and 1. And finally, the equivalent of this is itself x only. Okay, imagine you have x plus xy and simplified it to just x. Okay? That's how amazing simplification could be. Next is xy plus xy prime. So we use because there are common terms here in these two groups of variable. So we get the x because we can factor out the x, and then y plus y prime is actually equals to 1. Okay? And that is through uh, um uh identity number 7. So x and 1, and finally you will also have x. And then final example is if you have x plus x, x not x and y. So we can use the other type of distributive law, and that is number 15. Okay, since in this part is um you have you can distribute the x to the other term, so x, but now you you have this as the end already. So x and I'm sorry, x or x prime and x or y. So with this we can simplify because the x and x prime or not x is always equals to 1, so this is why this is 1, and then x plus or and or y, x or y. So if you simplify that, you only have, so 1 because of this, the 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 identity number 2, I'm sorry, the identity number 2, okay, is any variable that you end it with 1 will be itself. That's why you have the x and the y. Okay? So there are other, you can solve this and try to check if you can get it correct the same as this. Okay? With this example, you have x and x or y. You use, first one is you use the distributive, and then you use number 6, and then distributive again, then 3, and then 2. You have, finally you have x. Okay, and so on and so forth. So please study this part because this might come out in the exam. Okay, so those are the examples. We will end in this part of the video. For the next topics will be covered in the next video. Thank you so much for your time. Thank you for listening. Have a nice day. Bye.